have to go through this. Yep. So we tried to factor this. We factored first, and after we factor, we realized there's nothing to cancel out, not yet. So we keep our simplified format, it's the same. Do your domain restriction first. You always look to see what numbers can I not use, what is in there that I can't use. Find your restricted domain, and before you put in your calculator, look at it, but before you graph it, find your asymptotes. Use the sheet. The vertical asymptotes are the zeros left in the numerator after we reduce it, which we couldn't reduce. So we set the denominator equal to 0. That's a vertical asymptote. The horizontal asymptote has three things to test. It just tests the degree in the numerator compared to the degree in the denominator. If the degree in the numerator is less than the degree in the denominator, in this case it is, the less than that, we have no horizontal asymptote. When you have no horizontal asymptote, then you need to check for your slant. Your slant asymptote says the degree in the numerator is exactly one more than the denominator. So now we need to find the slant asymptote. So we synthetically divide this, set the denominator equal to 0, divide it, ignore the remainder. Because you do x2 over x1, this is going to be x1. It's going to give you an equation of a line. Now, a nice thing to do is put this in your y2. Because what it will do to your graph, it will draw your slant asymptote. And you will see that it guides your end behavior. If in fact it's not guiding your end behavior, then you did your slant asymptote wrong. You can put your horizontals in, but your verticals, no. You can't put that in your calculator. But you can kind of see those clearly. And on your table, they say error, so that's not too bad. Then keep going. Your zeros of the numerator. Those are your x-intercepts. Go to your numerator, we factored it, set them equal to 0. Confirm them on your calculator. Yeah, that's where they cross the x-axis. Don't forget your y-intercept. I like to go back to the original. I put my hand over the zeros. I'm -10 over -4, and that comes out to be +5/2. So, did it cross slightly above the 0 line? Yes, it is slightly above the origin. It is. My y-intercept does not line up to where I think my graph is, then I did something wrong. Once you have those, definitely do your sketch. Do your asymptotes. Now, sometimes what happens is, this guy right here, we can't see it. But you know it's there. Because whenever you have this condition, and you have a slant here, you know you got something down here, you know you have something up there. So you probably didn't see it on your calculator until you changed your windows. But we talked about this yesterday. If you looked in your table and you looked at these x values, it's there. It's just higher up. So make your y max go to 25, go to 30. Find it. It's there. If you have one piece here, the other piece has to be trapped inside of that as well. It's like your vertical angles. Remember your vertical angles? It's kind of like your vertical angles where they cross like this. If there's one here, there's got to be one on the other side of it. Do your max and your mins. Both of these are relatives because they're not the highest point, they're not the lowest point. Once you get these, now you can do your range. Your range says -infinity, come all the way up to this y value, which is this guy. Jump over it, start again here at this y value to infinity. You can't do your range until after. Now, if you keep them as parentheses instead of hard brackets, I kind of like that concept better, only because we round on this, so we never really hit that point where we rounded to. So if you don't give this to me as a hard bracket, that's absolutely fine. Or if you give it to me as a hard bracket because we ended it there, that's fine too. Increasing, decreasing, go off of your max and mins. So left to right, I'm increasing from negative infinity till this x value, right here. Then from that x value, whoops, I hit this wall, to this value, I am decreasing. Then I jump up here, I am decreasing from 4 to this x value, and then lastly, increasing from that x value to infinity. Just keep it going smoothly. Jump right, increase, right, decrease, and keep going from one to the other. I think it's easier if you're in a continuous motion rather than do the increase and say, oops, where is this increasing again? I think it's harder to jump back to that other one and find it. Concavities, this clearly makes a nice cave down. Negative infinity, whoops, hit the wall, 4. This clearly makes a nice cave up, 4 to infinity. Everybody has this? And why aren't you writing any of this down? Okay? You'll get the next one. Okay? The next one I didn't give you two. I gave you this one. This one should be a nice simple one. Right? Nice and easy. There's nothing to factor. I have a domain restriction. I look at my denominator. My x cannot be 1. I clearly see that in my table. Because when I look at 1 says error. Can't use it. So I come down. All my vertical asymptotes, zeros of my denominator there. And I saw that. I wasn't able to use 1. Makes an asymptote. Horizontal, the degree in the numerator, there is no variable in the numerator. So it's 0, yes.
Is there only relative minimum and maximum when you have a slant?
When you have a slant, you'll have a relative.
What if you don't have a slant?
Well, then it depends on where it goes. If it's a smooth line like this, you have no min and no max. Most of the time, you'll have no min and no max. The slant is what's pushing it back up again. So we consider these no min and no max, but we do consider them with concavity. So that is a very nice question to ask. So this guy technically is x to the 0 because that's 1. It doesn't exist up there at the x. So when it's less than the degree in the denominator, you automatically have y equals 0. Where is y equals 0? Where do I find that? What axis is it on? X. Good. It's on your x-axis. So now you know your asymptotes. Make your sketch. Use your asymptotes to guide your end behaviors. Your calculators don't always do a great job of this. You can put your y equals 0 and your y2. That's kind of, well, it actually won't help your y equals 0 because you probably won't see it. It can't write over the ones with color can. If you have a colored one, it writes over it. The color graphing calculators are so nice for this because it actually writes over it in color so you can see your asymptote. Okay, and don't forget, sometimes your calculators, they kind of do this. They kind of go up there and they stop. They just can't get any closer. It's too close for them. The colored ones will actually do a blue line right on your axis, or whatever color you choose. But always look in your table. You'll see what's happening to your y value. And I would put your table in decimals, not fractions. Because when they go in fractions, they're all different denominators. They're hard to tell. Domain and range. We had our domain. Our range says negative infinity. Whoops, can't do the 0. Jump over it and keep on going. This is both a decreasing from negative infinity till it hits this wall at 1, and then at 1 to infinity. And those are nice little concavities. Your x-intercepts, you had no 0, you had no x's, you had no zeros in your numerator, because you had no x's in your numerator. Questions on this one? This was a nice little one. Okay? You don't get it or you like it?
No.
Well, you don't get it because you don't work with it.
I don't care.
Well, then you got to start working it out. So if I walk this step by step with you, am I going to see you writing this down?
Yeah.
All right.
I wrote it down at first.
You did? All right. So, Gabe, can you factor that numerator?
No.
No. And we can't factor the denominator, so we can't factor and reduce. So, first thing we do, domain restriction. Domain restriction. Can't use 2. Take it out of your domain. Okay, always go for the domain first, because look what happens too. If there's nothing to reduce, that domain restriction is also your vertical asymptote. When I put it in my calculator and I look at my table, it says 2, error. Can't use 2. So that's going to say, whoops, don't go through me here. I'm putting up a wall. When you were starting to go towards my wall, whoops, either go down or whoops, either go up. You got to right alongside of it. You can't go through a vertical, ever. So I do my next test. My sheet says, degree in the numerator greater than the degree in the denominator. You have no horizontal asymptote. When you have none, you need to check for a slant. A slant said it's exactly 1 degree higher in the numerator. So to find your slant asymptote, we synthetically divide. And this is a nice, easy divide. Cross out your remainder. You don't care about it. Just go like this. Y equals whatever this has to be. It has to be x. Because it's always 1 more. 2 over 1, going to give you an x. 4 over 3, going to give you an x. So this, and all your asymptotes have been lines, right? So this is a slanted line that we're getting. So y equals x. That's the line that cuts through those quadrants, those 2 quadrants. Now, set up your graph. Here's your vertical asymptote. Here's your slanted asymptote. And if it helps you, put this in the y2. Put this in y2. You're going to seriously see that it's there. Plus, it really helps you see. If I can't see this part up here, I'm going to have to change my window. Because it's trapped in that slant. If it's in the bottom part of the slant, it's got to be in the top part of the slant. I think without putting your slant asymptote in your calculator, you might not catch that part. This one did fit on your 10 by 10. We look for your x-intercepts, the zeros in the numerator. Well, there's no real zeros in your numerator. You would have to do your quadratic or complete the square. So real simple, if you started to complete the square and you did 1 squared, so this would be like a plus 3 out here or plus 5 out here. As soon as you move this to the other side, you can't take the square root of a negative number. No real x-intercepts. Did your graph cross the x-axis? No. Has to make sense. Y-intercepts, go back to your original. It's going to be 4 over negative 2. Oh yeah, I can see a cross over here. I see a cross there. As a matter of fact, when I do that, that just happens to be my relative maximum right there at the 0, negative 2. And my relative min, this was a very nice one. They worked out very, very nicely. I think when they work out nicely, they're easier to do increasing, decreasing. Maybe the concept is a little easier. Good? Can everybody do the increasing, decreasing? Concavity? Talk to me now.
I don't know the concept.
Concavity. So you know what a cave looks like?
Yeah, like I know that.
Yeah. Well, this is an upside down cave. It goes up the other way.
So I just have to say from what point to what point?
So, yeah, from what x value? This came from infinity, right? Because it keeps on going forever. So, reading left to right, from negative infinity, I'm caving down if I hit the wall to 2.
That's all you have to say?
This is a cave down.
So what was all that stuff that
Cave
we do
up.
point like midway through?
That's your increasing, decreasing. Your increasing, decreasing work off of your relative mins and your relative max.
Well, I know I.
or your absolute.
Well, like when you know. Like,
Oh,
like,
inflection point.
Yeah,
That's when you did your polynomials.
So we don't
We
do that
have,
here?
not in this, because we don't have that in this. Your asymptote is what guides this. That's where I did this completely separate.
Okay.
I tested you on that part. This part's just rationals. Because kids get confused very easily, so I didn't want to do any confusing things here. All right, so what else do we have here? We have number 5. Number 5 was also a slant asymptote. Again, you could factor your numerator, but you couldn't reduce anything. Your numerator factored into perfect squares, and that gave us the zeros right here, the negative 1/2, the positive 1/2. So because it gave us a negative 1/2 and a positive 1/2, you could see that it dipped a little. If you didn't change your screen to see it, you can still do a minimum at that point. You can still do it. So you've got a relative minimum, you have a relative maximum, you have your slant asymptote, put that in your Y2. And I think you might this time might not have seen this piece down here. But if you put your slant asymptote in, if it's within this part of your slant, it has to be within the other part of your slant. And you'll see that if you looked at your table, you'll see values out there. So it's got to be hidden somewhere. So change your screen. Can everybody change your screen to see that? Did everybody find that point? Is there anybody that didn't find this maximum point? I'll gladly put it in my calculator. Okay. Can you do your concavities from there? Increasing, decreasing? Okay. So today, all right. So first thing we notice, we have a denominator. So let's take a look at your domain restrictions. Let's take a look at your domain restrictions. All right. So it says, this cannot be equal to 0. So I factor out an x. So I know x cannot be equal to 0, and x cannot be equal to 5. So your domain says, skip over those. Negative infinity to 0, skip over the 0. Go to the 5, skip over the 5, and to infinity. Okay. Now, we try and we reduce this. So we've got this. Is it possible to reduce anything here? What factor? X minus 5. Now, when you reduce this, this is key. Put a line through here, but put a little note here that this is your point of discontinuity. Otherwise, you will forget to go back to it. So write the reduced format of this. What's left in my numerator? If I take out that factor, 1 over x. This is my reduced function. Okay, now, because I have such a cool calculator now, I want to show you the difference between these. Let's graph your original one. Let's graph your original guy. Much nicer than my last one, huh? This is the Wabbit one for anybody that wants to put it on their own computer at home, or if you have a phone that's not an iPhone, you can put the Wabbit. It is W-A-B-B-I-T emulator. It's called Wabbit, and this is your 84 graphing calculator. So you can put this on your computer at home as well. So we graph. So cool, right? So I notice, I look at my domain restrictions, I see that I can't use 0, and I see that I can't use 5. Agree? Okay, now, I'm going to graph in here my reduced one. But I'm going to put a bubble thing out here so that we can watch it right over it. Like we did, whoops, I passed the bubble. Okay, so watch. Watch my graph writing over it. Do you see it? Isn't it the same graph?
Pretty short.
Pretty sure. So let's see. When I look at this, oh wow, this time I was able to use a 5. Why is that? Because I don't have 5 in my denominator, I took it out. So therefore, what was the only difference between this original one and my reduced one when I took out this point? I could use 5. This is the only thing that was different. That one little tiny point. That one little tiny point didn't exist in my first one because 5 was part of my denominator. Now, let me show you something else. I'm going to wipe out my second one just because we don't need this. But here's my original graph. And it looked the same. It said you can't use 5. 5 is an error. Can't use it. I look at my value. I say, what do you have for 5? It says, I have nothing for 5. I say, okay, what do you have for 4.999? 4.9999999. What do you have for that guy? Oh, I have 0.2. Oddly, do you remember that point that was in there before? Before I erased the second one? It was 0.2, wasn't it? So I say, okay, let me go the other way. What about 5.0000001? What's in there? Oh, it's 0.2. So you're actually learning your first concept, well, you've learned a few concepts, of calculus, where we talk about limits.
I'm not ready for calculus.
Well, yes, but you just did it, and you even saw the 0.2 out there. You said that as I approach that x value of 5, what would my y value be if, in fact, I could close that point? And you told me it would be 0.2. Algebraically, we say, okay, take the x minus 5, set this equal to 0, and we knew it was 5, then take this reduced format and find me what your y is. You're plugging in your x. Oh, this is 0.2. So this, in fact, is my point of discontinuity. My point that really doesn't exist. But we call this a removable point because, as we looked in the graph, we approached it from both sides to be 0.2. So if I could absolutely put my pen down and never pick it up, I could slide right over that 0.2. And in calculus, we do these as limits. And that's what, if you go on to calculus, that's what you'll learn about. So we kind of do a crude way of finding it, but we do find your point of discontinuity. Now, everything else works pretty much the same. We look at your zeros of your numerator. So if you graph this, where is my graph again? If you graph this guy, and I realize you really can't see it hitting if it hits the x-axis or not, but we can see that it's going to ride alongside that x-axis. You can kind of see that there are no zeros, right? It never crosses your x-axis. So we go here and we say zeros of the numerator. Well, there are no zeros in my numerator. So y-intercept. Y-intercept. You can do either one. Put a 0 in for the x. Can I ever have a 0 in my denominator? No. Well, I have no y-intercept. And didn't my graph say, it showed me, it never crossed that y-axis? right? It didn't cross the y-axis. So far, so good. So now, vertical asymptote. This is important. This is after I factored. Because x equals 5 does not give you a vertical asymptote, right? It was a removable point. But what's left in here? Oh, my x equals 0 was left in here. And can I clearly see x equals 0 at the y-axis was my asymptote? And my horizontal asymptote, same rules. You can go to either one. The numerator 1 over 2, less than that. The numerator 0 over 1, either one will work. Says if the numerator, degree in the numerator, is less than the degree in the denominator, then y is equal to 0.
And clearly we saw the x-axis as an asymptote because we couldn't find an x-intercept, right?
So now we can sketch. So we start our sketch with our asymptote. We've got a y equals 0. We have an x equals 0. And this is how we show your point of discontinuity. Your graph comes down, looks pretty nice. The graph comes down here, looks pretty nice. But somewhere, when x is 5, right here, you have a little open point. And that's how we show your point of discontinuity. We just put a little open point there. Your calculator cannot jump over it that finely. You see it in your table, but it cannot jump over a point of discontinuity. Because if you ever look at the lines on it, sometimes if you're really like too drastic of a slope, you'll see that it makes the lines actually like this as it goes. So they can't jump over a point of discontinuity. But we can certainly find it. Now, one thing that it does affect too is my range. It affects my domain, but we have it in there because we took care of your domain. But it also affects my range. If I could remove this point was at 5 and then 1/5 or 0.2, we can leave it at 0.2. So what's going to happen is now is I'm going to travel up, 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 up. I can't use a 0. That's where my natural asymptote is. I jump over it. Whoops, I got to jump over this point again. So what was the y value for this point if it was there? 0.2. So I'm going to go from 0 to 0.2, jump over that, and then from 0.2 to infinity. But that point does not exist. It's called a point of discontinuity. It doesn't exist. All right, and the rest of yours work the same. However, we have to remove that point. The point of discontinuity is a little bit annoying because let's do increasing, decreasing. Is this part of my function increasing or decreasing? Decreasing. From negative infinity to what x value? Where do I hit this wall? 0. Okay, is this part of my function increasing or decreasing? Decreasing. So we say, okay, it resumed at the 0. Uh-oh, it was decreasing, but that doesn't exist, so I have to jump over the 5 and then continue. So even in your increasing, decreasing, and your concavities, you have to eliminate or jump over that point of discontinuity. I had no increasing. Concave. Concave up. Concave down. So where's my concave down? What interval? Gabriel, what interval is my concave down?
Negative infinity.
Okay. To where? Where do I hit the wall?
What is it?
Follow it. Can't go past there. Where do I hit this wall?
0.
Good. Okay, now, this is my concave up. I'm concaving up in this area. So I come from where? 0. To where? Good, good. I can't use 5. And then from 5, I jump over it.
So
That's it. You found it. all you gotta do is kind of walk with it with your pencil. Put your pencil down and don't pick it up. Then you have to jump over an asymptote or jump over a point of discontinuity. Everything else basically works the same. The point of discontinuity is a little bit annoying because you see you took it out of increasing, decreasing. You took it out of all of those. So let's go to your homework page that we had last night and do that. Was it number 2 you couldn't do? All right, let's go to number 2.
It was number 2 and number 6 that we gave you. Actually, yeah. What's your number?
Okay, let's do number 2. It wasn't this. No. It was 6A. That's a pretty good one to do. So, let's factor. What are the factors of my numerator? So give me, how do I set this, how do I factor this into what? X plus 6, x minus 3. Agree? What's the factors of my denominator? Good. Okay, so let's hit our domain restriction first. First thing, before you factor, domain restriction. I mean, before you eliminate anything, domain restriction. So I look at my domain. I got 2 factors down here that I can't use if they're 0. So when x is 3 and when x is negative 2. So I'm going to jump over the negative 2, keep going till I hit the 3, jump over the 3. Okay. Now what factor can I reduce out of here? X minus 3. So I'm going to take out your x minus 3, and that's going to become what? Very nice. I'm going to make myself a note. This is my point of discontinuity. X minus 3 equals 0. I still can't use 3, but it's not going to be an asymptote. I'm going to remove it from being an asymptote. It's just going to be a little point. So I write my reduced function back down. I now am x plus 6 over x plus 2. So you know what, since we're at the point of discontinuity, let's solve for y. Let's see what that point would be. I take the 3, I plug it in. I get 9/5. So my point of discontinuity is this, 9/5. 1 4/5, which is the same as 1.8, right? 1.8. It just worked out in a fraction, so I just left it in a fraction. So now, vertical asymptote. My zeros that's left in my denominator. My point of discontinuity, I can remove it. But my x plus 2, oh, that stays. That I can't remove. My horizontal asymptote says clearly, when the numerator and the denominator have the same degree of the exponent, I take the ratio of 1 over 1. So now I can start graphing this. I can put this in my calculator. I'm going to see what it looks like, and I can absolutely graph this. Put your original one in here. Otherwise, you'll lose your point of discontinuity. Make sure you have your original one. Okay, and I can't see that I can't use 3, right? It's there, but I can't see it. I can clearly see the break at negative 2, right? Mm-hmm. I just can't see where my other one is. So let's write your asymptotes down. So that we can fit this in. So I have a y equals 1, and you know what? Put y equals 1 in your y2, and you'll see it makes a big difference. And x equals negative 2. So I clearly saw that I went like this, and I clearly saw that I went like this, but I noticed at the 3, sorry, I had a little open point. I had a point of discontinuity. And this is what I'm talking about with your calculator. If you come down here, and you can't put a vertical, but you can certainly put your horizontal one there, that'll help you. Do you see it? Do you see where your end behaviors are going? They're following that asymptote. They're following it. It's nice to have you follow it. Everybody good so far? Zeros of my numerator. I noticed I did pass the x-axis. So let me look for my x-intercept. Zeros of my numerator. After I factor. Yeah, and that totally makes sense to me. I'm crossing over here. Could very well be the negative 6, right? I could check it on my calculator and see negative 6, 0. Okay. Y-intercept. I do see that I crossed a y-intercept. Cover them up. 6 over 2 is what? 3. Oh, yeah. And that looks probably right. Oh, wait. My y-intercept can't be at 3. My point of discontinuity is at 3. Oh, it's probably sitting right on it's probably sitting right there. Y equals 3. Oh, yeah, that could very well be. It's at the y of 3. Sorry. I mixed it up with my x of 3. Okay. So we've got all the pieces that we need. So now let's do our range. Remember, don't do your range until after you find any max or mins and you point to discontinuities. Do I have any max or mins? No max, no mins. So my range says I'm going all the way up till I hit this y. What is this y? 1. Then I'm going to jump over it, but I'm going to get stuck again. Because I got to jump over that 9/5, which is greater than 1. Then from 9/5 to infinity, I'm good. Okay? And all you have left is your increasing, decreasing, and your concavities. So let's do an increasing, decreasing. Do we have any increasing sections of this? Is y increasing at all? No. Decreasing from negative infinity to where? To negative 2. Then it's decreasing from where? Gave negative 2 to where? Decreasing with the x. The y is decreasing, but I gave it to you from x. Negative 2 to where am I going to get stopped? Oh, what's this x value? 3. I got to jump over it, and then 3 to infinity. I got to jump over the point that doesn't exist. And again, clearly, if you look at your calculator and you do a value on this, and you say, where are you at 3? It says you don't have a point at 3. There's no point. But if I look at 3.000001, it should be really darn close to that 1.8, isn't it? That's because I can remove it at that point. I approach it from both sides. Okay, so let me give you homework for tonight.